what we are going to be learn on this today's live is complete guide to RTOS task and thread management. So this is what this today's live is gonna be happen. Okay. And regarding that, first of all, we are going to be understood the concept of task and thread concept and task priority. So this two concept only we are going to be study on today. Okay. First of all, we need to be understand what is task in RTOS. Okay. So we most probably we are going to be use the word code as in task and thread. So what it actually meant. Okay. So what is actually we call it as a task, what we actually call it as a thread. So we need to be understood this concept. For that, we are going to be understand what is task. So you can either call one instruction or whatever it is, you can either call task or thread. It is your wish. Okay, it's an independent execution contest with its own. That means it is one of the contest. Like you are it just like an instruction. Okay, task is just the instruction. Okay, it just want to be processed into your any processor. Okay, for that, how this RTOS is actually going to be helping out. Okay, so that is the difference. So you are having the different kind of task, whatever the task it could be, and how this RTOS is actually going to be help you to process the task. Okay, for if you want to be execute the task, you need the contest called as and you need the registers and counters. Okay, so whatever it is, if you want to be storing the data, okay, if you want to be temporarily storing the data, so there is a difference. Is that if you want to be storing the data, you will use the memory. If you want to be temporarily storing, if you want to be storing the bits of data, you use the registers. If you want to be counting the data, so you are going to be using the counters. So kind of many parameters which is present in your microcontroller. Okay, so when I can use these counters and when so if you want to be understood this concept, you definitely understood the concept of microcontroller. So what this microcontroller which is having inside this, okay, like what are the registers actually inside in your microcontroller, what are the memories actually inside in your microcontroller, and what are the counters actually inside your microcontroller. So here I'm just showing you the common microcontroller, like common registers, counters and memories which is present in the RISC based architecture so of microcontroller. So why we implementing, why we talk about this RISC based architecture? Most of your microcontroller which is based on RISC based architecture, right, it is a reduced instruction set, right? So if you have missed out this, you just watch out this video. And here I just mentioned here the common registers and counter, guys. No need to be confusing you, because other than that, we are having a lot of registers and counters, memories are there. Here I'm just showing you the common counters register which is going to be used in your microcontroller. First of all, we need to be understood the program counter. What is program counter and when we are going to be use this program counter and where? So this program counter is one of the counter. So when I'm going to be use this one is, so you just simply see you are having the multiple instructions. Okay, so you are having a multiple instruction in your memory. Okay, this is how you are having an instruction in it. So what is this purpose of, what is the purpose of this program counter is, so we call it as an PC. The program counter purpose is it helps to be hold the next instruction address. So first of all, this is my task. Okay, I call it as a task 1, and this is task 2 and task 3. I'm having around 4 tasks. I need to be get process every task one by one. Okay, first of all, I just took this task and processed. This task has been completed. If I want to be get this process, okay, if I want to be process this task too, I need to be acknowledge what is the next task I need to be processed here. Okay, so in this case, I need to be hold this address because this embedded system, so each and every registers, each and every memory, each and every peripheral which can holding the individual address. Okay, we other than that, it is having the base address, we call it as. Okay, so why we I'm going to be use this one is, first of all, the task one which is having some address. Okay, for example, fh. So this is not the permanent. I'm just telling for sample address. Okay, so this is the address for task one, and address two task 2 address is HX. So example, I'm just telling you. Okay, and 0 cross EEH and 0 cross 1 C0. Okay. So I'm having these are the address for each and every one. So first of all, once this task has been completed, so what is the purpose of this program counter? It should be hold the next instruction address. So here the program counter, which is always holding the next instruction address. So once this task has been completed, so it always, when it is processing, it priorly just holding the address of the second instruction. So once it has been completed, once this has been completed, you just erase and update the third instruction address. And then once it has been completed, it will be update the fourth instruction address. So what is the main purpose is it just holding the address of this next instructions. So that is the main motto of this program counter. Likewise, we are having the multiple registers and program counter. What is the purpose of stack pointer is it points the top of the task stack to keep its local data and return address. So you need to be understood one concept, the memory layout concept. Whatever the memory you're going to be taking, especially if you are taking a RAM, it's just having the memory layout of different sections, dot data, dot text, dot BSS, and heap and stack. Okay, so what it actually means is, so whatever the data, whatever you're going to be written into this program, so depends on your variable you have been using. So it is going to be using the different sections, okay, in this memory layout, which can using a different sections to be storing your data. Okay, here I'm having a different section called as entire data kind of thing. So mainly just using a stack memory, most of the data going to be stored, because your local variables, your local function calls and return address are all the thing is going to be stored in the stack. Okay, so it is starting to store from top of this address. So it is going to be stored like this. Okay. And then CPU register set. So what this purpose of this CPU register set is, so task working variable must be saved and be restored. So this is a very important concept you must be understood. So when you're going to be switching the task from one place to another place, like one memory to another memory, memory to any processor, if you're just switching the task means you're going to be all the data has been initialized in your program. So when you're going to be run, all the data going to be stored based on your section, right? Whether it is dot data, dot bss, dot text, dot heap, or stack. So depends on this memory layout. All if you are using a uninitialized global variable, it is going to be stored in any of the layout. Okay, and kind of array is going to be stored in the heap. So your local variables is going to be stored in stack. So initialized data going to be stored in different data kind of layout it is going to be stored. Okay, so after that, once it is going to be run, it is going to be switched from memory to any processor. So this time it need to be stored all the data. Temporarily, this need to be stored the data. So how the data has been stored? So kind of structure you need to be know that all the data is going to be stored in the CPU register set. Okay, it is going to be store your data. So how you are having that data? So it is going to be stored in the same app. Because once it is going to be restored, that means once it just move back to its original state, it need to be restored all the data, right? So for that, we are going to be using the CPU register set and then stack memory. The stack memory purpose is private RAM area where each task store local variable. Yes. So previously we discussed about the stack memory purposes. It is going to be store all the local variable, return address, and stave register going to be stored. And then priority level. What does meaning priority level? So in this task, this priority level is very, very important concept. Like if you just see this one. So if you are taking any peripheral, guys, if you want to be processed any peripheral, you definitely required the thing called as an priority number. Okay, for example, you are having a UART, I2C, SPI kind of task you are having, like ADC kind of task you are having. So each and everything should have some priority level. So based on this, you can segregate which is going to be processed first, which is going to be processed second, and third, you can segregate by the priority number. Okay, so this is very, very important things in it. Okay, so that is the priority number. And finally, we are going to be especially discuss about the state information. What is meant by state information is, yes, so if you are taking one task, okay, if you need to be understand what is the actual current state of the task, whether it is getting ready to be processed, whether it is actually running already in the processor, whether it is in blocked state, whether it is in waiting state or terminate state. So this is called as in state information. If you are taking one task, if you are taking one task one, if you need to be understand what is the actual purpose, what is the actual state of this task, we are going to be segregating by the different stage. Okay, so in this case, so if you just see this one, they are going to be see the task states in it. Okay, for the task status, it just having the what the state it is actually currently right now. Okay, so now I'm just show you the thing. You just see this. This is one of the tasks. Okay, for example, I'm just taking so task. So I'm just simply taking this is my task. Okay, so this is my task. So this task, what is the actual purpose of this task? Whether it is ready or whether it is running, whether it is blocked. Okay, and blocked and waiting is both the same condition or terminated. So these are the tasks we are going to be call it as. Okay, so how can I differentiate whether it is ready or okay? So first of all, you're going to be see about the ready state. So what is ready state is? Task is now ready to be executed into the CPU. Okay, so all the resources are needed to available and waiting in the ready queue based on the priority can transition to be running when scheduled. Okay, so what it actually means is, so this time the ready state which is meant, it is all the resources which is ready. That means, so what are the registers? It has been stored, all the register has been given the data. So it just holding all the data. It is all has been waiting in the queue. The task one is waiting in the queue. So when the processor, but it is not enter into the processor, just in the waiting state. Okay. So when the processor has been called, so it just move to this processor and get processed. Okay. This state is called as a ready state. So all the resources. So like whatever the registers it has been required, all the registers has been given the data and it has been allocated. Only it need to be scheduled into the processor and it need to be processed. That is called as a ready state. So this state is all the resources are available and waiting in the ready queue. So ready queue means just waiting in the queue based on the priority. So because not only this task when kind of many tasks will be available. So kind of task, many tasks gonna be available there. Okay, so likewise many tasks is going to be available like this. All the resources has been done, it is just waiting here. So when the CPU is called, so just go to this and processed here. Okay, this is called as a ready state. And what about this running status? This running state is different, like task is currently running, like executing. Okay, so previously I told you, so when it is ready, so it is going to be scheduled and then processed here. Okay, so your processor will just taking the task one. First of all, I'm just taking this task one and it just started to be process your data. So what the process is actually going to be done. For example, I need to be UART configuration. So I'm doing collecting the data through UART protocol simply. So you just simply collecting. So the process has been done. So process has been started to be work on. So that is called as a running state. Okay. So this is called as a running. Currently, your process is currently get processing here. And then blocked or waiting state. So either we call it as a blocked or waiting state. What it does actually mean is task cannot proceed until some event going to be occurs, removed from the ready queue to save scheduling overhead. So what you are going to be mean here it is, so when you are going to be look out some blocking reasons, so what are the examples for blocking or waiting states, you can able to understood this concept. Okay, so these are the reasons. So first of all, waiting for semaphores or mutex. So if you can't understood this concept, what is semaphore or mutex, I'm going to be explain this concept. Okay. So the you just understood what is waiting and blocked state. So why we call it as a blocked or waiting state in it. First of all, task passes until it successfully acquires a lock or resources. For example, if you just look at it, I'm having a 2 UART protocol. Okay. In this case, I already explained this. All the tasks is gonna be happened based on your priority number. Okay. So if you just look out the task, I'm having a 5 task here. Okay. So this task. So first of all, this is having a higher priority task, and then this is the second one. So 1, 2, 3, 4, and 5. So this is how the task has been arranged. Okay. So here I'm just simply, I don't want to confuse with this one. So simply you just consider this is task 1 and task 2, task 3, task 4, task 1. Here what I'm going to be do is, so I already assigned, so this is the first task going to be run first. Second going to be, okay, so this is how it has been arranged. In this case, based on the priority number, it is going to be happen. For example, UART. Okay, UART is currently running state. It was waited in the queue. So currently, just give the processor and the processor started to be processing the data. In this case, if it is I2C, if you want to be trying to be configure I2C, it is conflict, right? Because we currently UART is processing. If I2C trying to be get processed, it is going to be conflict. This, if avoiding those concepts, you are going to be putting the priority levels. So you are going to be check which one is having a higher priority. For example, you are having a 3 is the priority. Okay. But it is having a 1. Okay. So always the lower number which is having higher priority, higher number which is having a lower priority. Based on this RTOS going to be varies, guys. Free RTOS, this condition. If you're using a ThreadX and kind of thing, it is going to be different. I'm going to be tell it. Okay. For example, you want 3. It is having a priority number of 3. 3 is a lesser priority. Okay. And I2C, it is having a priority number of 1. It is having a higher priority. Okay. So this time, what the processor can do? So UART is currently working. What it actually going to be do is it just preempt the UART. What is meant by preempt? So I already told you this. So what is the meaning of preempt? So the preempt meaning is if currently one task is processing. Okay. If another priority task is coming, but it is having a higher priority comparatively your current working thing. Current task, he just stop this current task that is called as a preempt. He just neglect that current task and giving priority to the highest one. Okay, and then it is started to be processed here. This is the actual thing always gonna be happen in RTOS. Okay, that's what it is efficient. Your RTOS is efficient. Real-time operating system is efficient. So in this case, if you just look out at, I'm just bringing the concept example. You are having a 2 art UART here. So consider your task 1 is also UART. Your task 2 is also UART. Currently, your task 1 is processing. If again the UART is trying to be conflict, what it actually going to be do? Whether it is giving a priority to them or not? No. Definitely both are having a same priority number. One should definitely going to be wait. Right? So this waiting state is gonna be called as an either blocked state or it is going to be called as an waiting state. Okay, so this is one of the example, and another one is a delay or sleep operation. So what it actually means, delay or sleep operation is, so if, for example, You are going to be taking one sensor. Okay, you are just taking one sensor. That is your any sensor you can say. Take it. Soil moisture sensor. I'm just taking one example. Or temperature sensor, any sensor. So if I want to be, this is one of the sensor, I need to be collecting the data from my sensor. So in program, how we are going to be written the code. So I'm going to be write a code as and I need to be write one function to be configure this. So for example, this is analog read. So the specific pin I'm in configure 14th pin. So I need to be collect the data from those one. Okay. So for what I'm going to be do is, so I need to be collect the data and the data I'm going to be printed on this printer function. Okay. Need to be printed on here. So in this case, you are going to be written one delay or sleep. In C, we are going to be using a delay. In Python, we are going to be using a sleep. Okay. So don't worry about that. So both are doing a same functionality. And here you are going to be use one delay function, going to be make some stop, not exactly stop, some waiting condition. For example, in soil moisture sensor, you are going to be collecting the data, going to be understood what is the level of the soil. Okay, whether it is having wet, dry, or moisture level, going to be understood. So first of all, you are going to be allocated in the analog data 100 from you are going to be collecting the data from 100 to 1000. So meanwhile, you're going to be collecting the data. For first example, so you have been collected the data called in first one is 400. So second data you're going to be collected. So that is the difference. That means first data I've been got 400. Okay, and what is the next data? What is the duration of the next data you're going to be captured? Whether it is 1 second or 1 millisecond kind of thing, right? So if you are getting the first one is 400, second data you're going to be get 500, for example. So what is the duration? What is the time difference between you're going to be get the next data? Okay, what the gap, what the duration required? Okay, so for example, I'm just putting 1 second. Here is the 1 second is your blocked or waiting state. Next, you are just simply getting 700 is the next data. What is the duration? Same 1 second. So that 1 second is your blocked or waiting state. Okay. And then messages, the waiting for the message queue data. That means here it is example for you are just collecting the data for any LCD. Okay. Because most of the sensors you can collect the data from the sensor. That is the sensor going to be do. But this kind of LCD, you are going to be give the data. It is going to be print the data on your LCD board, right? So if you first of all, you just give the data called as an hello, okay. And second, you are trying to give the data called as an word. So the duration between hello to word, that is going to be called as an waiting or blocked state. And then waiting for input and output operation. That means you are having the multiple peripherals. Okay, you are going to be configuring like a DMA and interrupt at the same time. So you are having SPI also. There is a three peripherals here. So you have been assigned DMA and interrupt when it has actually completed this data, completed this process. You just SPI are going to be transferring the data. That means it is one of the communication protocol. Right. So here, the waiting state of SPI is gonna be called as a blocked or waiting state. Okay. And finally, is the event flag waiting. Here, because why I'm telling those example is because these are the waiting or blocked state in RTOS. Okay, so whenever the small delay which is happening, so whenever the data transfer, so meanwhile another peripheral is waiting. So those who are waiting, that state is called as a waiting state. The task which is in the state of waiting or in blocked state. Okay, here another example is the task, okay, you're going to be connected with the GPS and both your Wi-Fi going to be connected and send the data to your cloud. So this is your, so the waiting for the Wi-Fi, waiting for GPS going to be connected. This waiting state is also going to be called as an blocked or waiting state. Okay, I hope you got clear. So most of those clear concept is got clear. Okay, this is the complete blocked and waiting state. And what about the suspended state? Suspended state is simple. Okay, so the another task, the suspended state which can able to suspend by itself or another task. So very good example is if you just look out it here, suspended state is happening here. Okay, so if you just look out here, it's explicitly suspended by another task. Okay, or itself. Okay, so if any other task which is coming, okay, here it is actually doing by itself. Okay, because UART1 is actually processing here. Right, so UART1 is already is processing. This UART2 is actually suspended. Okay, so it was spending itself, okay, because it just stop, okay, just stopping itself. Okay, so or else it's just doing by another thing, but not eligible for scheduling, so requires explicit resume operation and different from the blocked state. Okay, so other than that, okay, it is not exactly like your blocked or this one state. It just resumed it. Okay, so it is not going to be waited. It is started to be a stopping itself. Okay, so okay, at the time it is called as a suspended state. Okay, and then finally terminated state. So what does mean by terminated is once the task has been completely done. So when you're going to be completed the task, it is going to be called as, and all the resources are not going to be cleaned up. The registers data going to be cleaned up, and everything is going to be comes down, and TCP going to be deallocated. Okay, we are going to be study this TCP on tomorrow. So the state transition, this is how it is actually going to be looks like, guys. Okay, if you just see this one, it is going to be create. If you are creating one task, it is going to be create, and it is ready for the task going to be run, and then it is going to be the processes get run. Okay, and whether it is get blocked or suspend, so you can able to block, that means you just put it on waiting state or just stopping itself, resumed it is it itself. Okay, it is called as a suspend state. And yeah, that is the thing. And finally, once you're blocked and suspended gonna be happen, it just terminated. That means your process has been completed. It just went for the terminated state. So this is the state called as an once your task concept and state. So what is task? And what are the states of your task? So that is what we have been discussed. And then we are going to be discuss about the concept called as a task priorities. What are the task priorities we are just having? Okay. So first of all, we need to be understand in our task, one of the most important job, okay, is the task. How we can able to run the task. Okay, which one is going to be actually run first? So which is going to be run second? So kind of a differentiate, kind of allocations we are going to be putting, right? So if you are having the 100 tasks, here we simply showing 5 kind of thing. If you are having 100 tasks, the you need to be allocating which one going to be runs first, which one going to be run second, kind of thing is very, very important. How it is actually going to be happen? Based on the priority is going to be happen. Okay, so this job is called as a priority system. If you are having thousands of tasks, which is going to be happens first and second, next job going to be determined. Okay, so if you want to be understood this concept, you need that property. That system is called as a priority system. Here, by giving the CPU time to be higher priority task first, the system can respond quickly and efficiently in real time. Okay, so that thing, so because higher priority, we always require the higher priority. That means the first priority. Okay, so we are having two types of priority scheduling, guys. What it means by priority scheduling, I already told you need to give the priority based on, so which one is having a higher priority, that is going to be runs first, lower priority second. That is the thing. But here the priority which is having a two type, one is called as a fixed, another one is called as a dynamic. What it actually means, what is fixed priority is, first we will look at the characteristics of fixed priority. What are the characteristics is, if you are using a fixed priority, each task is assigned the static priority at the creation. Okay, what it actually means. So, for example, I'm having a multiple task. Okay, I'm having a multiple task. Okay, in this case, I already told if you are having a processing UART, for example, if a UART is coming as a another priority task. So, what it actually do? Just preempt. Preempt means you just stop the UART giving a priority to this I2C. Why? Because it's just having higher priority rather than this. So in this case, you're just doing a normal priority system. If it is a fixed priority system, you can't do this one because you should schedule it priorly with the priority number. So which is actually going to be happens first, which is happens second, which is happens third. Kind of priority you need to be do it first. Priority doesn't change during execution. So this is the mandatory thing. So when it is a fixed priority task, it is not going to be changed while at the time of execution. Okay. So that is the mandatory thing on it here. Okay, most commonly in real-time system, it is predictable and analyzable behavior. Because just think about it. If you are having a multiple task going to be get processed, if it is a normal one, your normal priority system, if it is you are processing, so if it is any other trying to be preempt, it just giving it. Okay, it just preempt the current task and another task get prioritizing. So if it is a fixed priority task, it can't able to do this, right? Because it is already scheduled with the priority number. It can't able to changing at the execution time. That is the characteristic and priority level. So it is very, very important concept. So if you just look out at every microcontroller which is having a priority number, like those kind of range. So if you want to be look out at, I just showing one microcontroller priority number. For example, I'm just opening up the reference manual of STM32 microcontroller. So if you just open up the page of nested vector table, so you can able to see the priority number. For example, this is called as an all priority number. Okay, like if I'm just seeing this timer 2, which is having a priority number of 35. Okay, and SPI1, it is having a priority number of 42. And UART1 is just having a priority number of 44. So based on this priority number, it is going to be distinguish your priorities. But in this case, guys, we are having the different types. You need to be understood this concept because if you're just implementing the free RTOS in your, if you are trying to implementing the free RTOS or VX works, lower number which is having a higher priority. Like in this case, here also. So for example, you just taking the random one like timer 3, priority number of 36. UART1, priority number of 44. Here, the timer 3 is 36. Okay. And UART1, it is having a 44. Here, the lower number is having a higher priority. 36 is having a higher priority comparatively of 44 of UART1. That is called as in priority numbers. Okay, so it is worked, the free RTOS which is taking based on this concept. So your lower priority which is having a lower number which is having a higher priority. Okay, if you're just taking the ThreadX and if you are trying to implement this kind of RTOS like ThreadX and some different RTOS is there, and how it is actually taking us, your higher number is just having a higher priority. So it is in ulta, like 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 uh, like 44 just having a higher priority comparatively 36. So which is happening in the ThreadX. So if you're taking the free RTOS and VX works, it is lower number, it is having a higher priority. Okay. So this is the concept in it. And next, we need to be understood what is preemptive priority scheduling. What is meant by preemptive priority scheduling? So I'm going to be tell you this concept on here. Yeah, preemptive means if it is happened based on the fixed priority. Okay. So if it is based on this fixed priority, so both the things happen, guys. If it is fixed priority or can change the priority number means, yeah. So each and every peripheral is just having a specific priority number. If you want to be change it, yes, you can change the priority number. For temporarily, we can able to do this. Okay. If you are using a fixed priority task, if you want to be schedule the task with the priority number, yes, you can able to schedule with the random priority numbers is applicable. Okay. So here, if you just see this one, preemptive priority scheduling, what it is mean? You are going to be based on the fixed period. Fixed means you are going to be allocated. You are going to be this is my task. It is having this priority number. That means it is having higher priority. Okay, so that's how you are going to be allocated like this. So this is a medium priority. This is a lower priority. Okay, so this is how you are going to be allocated with a priority number. So here the priority number is very important concept on here. Okay, another very important concept is your time slicing. That is a round robin technique. Why they are going to be introducing this round robin technique, round robin algorithm here is, so it is one of the crucial thing, guys. Because if you are having the multiple tasks having an equal priority, so the CPU will be confused. So here also I tell you the one example, guys. I'm having a processing my UART. Another UART is actually trying to be preempt. Okay, what it actually going to be do? You don't consider this I2C right now. You just forget it. Okay. Here, I'm having a UART. Currently, UART is currently processing into your processor. Okay. So, another task which is coming, this is task 1 and this is task 2. This task 2 which is called as a same UART. What I told you already, second task is actually going to be waited. That is called as a blocked or waiting state. This time, this waiting state, right? So we can also implement it another technique that is called as an round robin technique, round robin algorithm. So what it actually means is this algorithm, which is going to be help you to be slicing your time. So slicing the time means the processor which can slicing your task. So for example, I'm having a task 1 and task 2. Here also I'm trying to be explain with the task example. If you just look out it, task A and task B. Okay, both as your UART. Okay, here task 1 and task 2, both as your UART. In this scenario, okay, what it actually going to be do? One is definitely going to be waiting. So instead of putting into the waiting state, what I'm going to be implement here it is, I'm implemented the round robin technique. So here when I'm going to be write the code, UART 1, task 1, you're just taking 10 milliseconds to do your process, and task 2, you're just taking 10 milliseconds to do your process. Okay, it started to be work on this. Okay, the UART 1 is started to be taking 10 milliseconds to be processed. If it is can't completed with this duration, it just definitely stop its work and give the authority to this task 2. Okay, it will be taking 10 milliseconds. If can't able to done this process, definitely, even though whether it is completed as task within this timeline or not, it is not going to be considered. When the time is meeting the 10 millisecond, it is going to be given the complete authority to the second task. Okay, then you can ask me, it is going to be, yes, it is sharing the timing. So based on this priority, it is not actually going to be putting on the waiting or kind of say. So it is going to be sharing the time. Okay, so task 1 is just taking 10 milliseconds, even though whether it is completed the task within this timeline or not, you just switch it from this to this. So after just taking this time, so if it is not, so repeatedly it is going to be happen. So that thing is repeatedly this task is going to be happen. So there is no problem for any of the tasks, because every task has been included here. Everyone is taking the specific individual time. So within this timeline, it is going to be completed as task. Okay. Within this duration, it is trying to be completed. If it's not, it is try to repeat it as cycle. Okay. That is the round robin technique. And now we are going to be discuss about the mutex, because previously while I'm going to be teach you that concept, I told you some example. I told one concept called as a mutex. In upcoming classes, we are going to be detailed discuss about the mutex, summa pose, and kind of concept. Okay. So what does mean by mutex is? Yes, the full form is mutual exclusion. It is a mutual exclusion. So mutex is called as one of the lock, guys. So lock means what? Okay, it's like a lock and key. Like no, so it's just like if you're just having one task, I'm having two tasks. Okay, I'm having the multiple tasks like this. First of all, this is my task one. This is my task two, task three. Task kind of task is there. In this time, task one, which requires some shared resource. I mean, it needs the data from registers, right? Because all your data are going to be stored in your registers, memories and all. Okay, so kind of CPU registers, kind of many registers is there. So this time, what can I do? What can I do? So if all the tasks required your resources, kind of, so you just taking a CPU registers, stack memories, stack pointer, kind of, all has been there. So your task is required from task one required the resources from every registers and memory. The task two is also going to be required from every registers and memory. Task three also there. So if all the tasks are trying to be get the data from memories and register kind of thing, a complete thing is going to be get crash, right? So it is going to be overload. So for this, what we are going to be introducing is mutex. It is like a lock. It's just a key. Okay. So those who are having the key. So whenever if the task one is processing, you just put the lock. That is called as synchronization. Okay. The mutex means it's just lock. No need to be confused. You just consider it's just a lock. So whenever we are going to be using the mutex with the task one, you just logging the task one. So when it is like get locked, the task one can able to access all the resources. Okay, all the resources and went for the and go for the processing. Okay. So next that the mutex is trying to be locked to this task 2, then the task 2 can able to access all the resources. So it is going to be happen in the scheduled manner. So the mutex is very, very important thing, because here you can able to understand only one task can able to share all the resources at the time. Okay. So this is the thing, guys, you can able to understood this concept. So especially it is in the synchronization. So only one task at the time can able to resources, like such as you or I to see whatever it is going to be resource sharing the stuff. And then real-time example. So we go with this real-time example. The main purpose is it can able to prevent the data corruption and race conditions. So when the multiple trusts trying to be access the same resources simultaneously, going to be happen the data corruptions, right? So avoiding this concept, we are going to be introducing the mutex in it. So now we have been discussed about the mutex. Now we are going to discuss about the priority inversion problem. So what is mean by this priority inversion problem? Okay. Okay, so we are going to be discuss this priority inversion problem is okay. I've been allocated the thing. Okay, so we have been discussing about the fixed priority, right? Previously, I've been discussed about the fixed priority. What is mean by fixed priority? So it has been fixed. Okay, so if it is a fixed priority, it has been fixed like this. So I'm being assigned. I've been scheduled with the priority number. Okay, so task one is having a priority number of this. So you're going to be you're going to be process first. Task 2, you're going to be do second. So it is having a priority number of 2. 1 kind of thing. Just think about it. So I've been scheduled, it is fixed. If it is emergency, higher priority task is trying to be interrupt, can't able to interface with this because even though you are having a multiple task, it is trying to be interrupt. It can't able to do this process in it. Okay, so it should be wait because it is a fixed priority. What can I able to do this one? So it can cause a problem. Yes, it causes a priority inversion problem might be happens because when the higher priority task is trying to be interrupt, it can't able to interface with this. It is trying to be blocking. It is trying to block it. So this is called as a priority inversion problem. So your higher priority task blocked on mutex healed by the lower priority task. So in this case, so you are just fixed, you are just previously allocated the task and each has taking the mutex. So your mutex is also get by the fixed priority one. So which is going to be do first and then second, third. By because it's just locking the task. If higher priority task which is trying to be interrupt, it can't able to do this. It is causing a priority inversion problem. Okay, so this is how it is going to be too. So when the higher priority tasks get blocked and then lower priority going to be happen. So this problem, avoiding this problem, what can able to do this? So that is what we are going to be discuss. Okay, before that we are going to be discuss about the dynamic priority scheduling. Okay, so we are going to be discuss without priority inheritance concept later on this one. First of all, we will discuss this what is dynamic priority scheduling. Okay. So why this dynamic priority scheduling is coming here it is to avoiding this priority inversion problem. We bringing this dynamic priority scheduling with this different setup. Okay, like priority inheritance. So what is this priority inheritance is? Your lower priority task which is temporarily inheritance the higher priority holding the sharing resources. That is prevents the unbounded priority inversion. So with this priority inheritance, what it actually going to be happen? That is thing we are going to be discussing. Okay. First of all, L as a mutex. So for example, this is the lower priority. Comparatively higher priority, it is lower priority. Okay. So it just having a mutex. That means it just locking your lower priority. That means it can only get the all the resources to be get processed. But higher priority requires the mutex because it need to be do the process here, but it can't able to do this. So when the lower priority releases the mutex, then only it can able to process here, right? So this time what the H is trying to be taking the mutex, but it can't. So this time what your operating system is going to be do is your temporarily the L priority is going to be rises up to the higher priority. That means you are having the lower priority. The higher priority number is like 5, for example. What it actually going to be do is your lower priority temporarily it is going to be rise the number called as in 5. So this time you are having a lower priority, medium priority and higher. So this is how the segregation going to be happen. Okay, so when you're going to be rising your lower priority up to this higher priority, like 1 to 5, so it's just looking as a higher priority. So once this task has been completed, so it automatically give the mutex. It automatically give the mutex to this higher priority one. So this medium priority can't able to preempt. Okay, so it is not able to involve here. It automatically give the mutex to this higher priority one. Okay, so we are temporarily doing this one. So now M cannot preempt. So L gets the CPU and finishes its works. So mutex, so a higher priority task. So L releases the mutex and it priority drops to normal. So once it give the mutex to this one, so it again move back to the 5 to 1. Okay, it again move back to this original priority level. Okay, and H immediately acquires the mutex and continue running. So it just temporarily doing this thing, guys. Okay, because lower priority and then medium priority kind of thing is actually going to be allocated already. If the lower priority is just having a mutex, you're just raising the value up to the called as an higher priority level. So you're just trying to be switch the It's just trying to be switched once it has been completed because both are same 5 5. So once it has been completed its task, it is not going to be come to this medium priority and all. You just directly switch to the higher priority. It just automatically give the mutex to this higher priority of 5. Okay, so this is how it is actually going to be happen. It is called as a priority inheritance. And then again, another technique is also there. It is called as a priority ceiling uh, protocol. So same thing, guys. Same thing. It is going to be happen. Okay, it is also trying to be evaluate your priority number. It is also going to be helps to be elevate your number to be giving a priority to a higher priority. So when your task takes the mutex, that is a log, automatically evaluate your ceiling priority, the highest priority one. That time it is going, the medium priority cannot be preempt. It is once the lower priority task, you just give the mutex, automatically higher priority going to be take your lower priority again move back to its original state. So if you just see with this example, you can able to understand this concept. First of all, I'm having a priority numbers. Okay, in starting stage, lower priority number is 1. Medium priority is 3. Higher priority is 5. No, don't look out this concept called as in whether it is 3 hour task, VX work kind of thing. So you just see this example. Okay. Lower priority number is 1. Medium is 3. Higher is 5. So L took the mutex. That means it just taking the authority, the lock. So at the time, just look out it just trying to be change its priority number from 1 to 5 because higher priority need the mutex. This time it is switching the priority number 1 from 1 to 5. Okay, so what is actually going to be happen? So once this releases this mutex, it just directly go to this hedge, not him. So we can able to saving the time. So you are just seeing there is 3 tasks here. Kind of you are having the multiple tasks will be allocated. So avoiding this priority inversion, we are going to be introducing this one and it just changing this number. And once the task has been completed, it just releases the mutex. Once it has been releases its mutex, come back to its original number of 1. Okay, so this is called as a priority inheritance or priority ceiling, guys. Okay, and if you're not without priority inheritance, what will be happen? So your lower priority has taken the mutex and higher priority now need the same mutex because higher priority trying to be interrupt, but it never get the mutex in it because it definitely going to be waited for to be get the mutex. Meanwhile, the medium priority get the mutex and start to be works. So L doesn't get any CPU time to be finishes off because all the CPU time going to be wasted. So the higher priority task cannot get the mutex. Problem is going to be happen. So H is get blocked here. So more than long time. So this is called as a priority inversion. To avoiding this one, we are going to be introducing the priority inheritance and ceiling techniques to be temporarily we are going to be changing the priority number to be interrupt with them. Okay. And finally, okay, last thing, not least, it is a deadline based scheduling. What are the deadline based scheduling is? Earliest deadline first. That means whenever you are having a task, that task which is having a nearer deadline. So if you are having a task which is going to be completed with this duration, okay. So if you are having a deadline kind of this kind of duration, so you need to be completed with this time. So you are going to be giving the priority to this one. So then fixed, that means whatever the priority which can able to do done by the shorter time. Okay, so if you are taking two number, two tasks, okay, so that two tasks which can able to done by one can able to done by the shorter time, so you can done that one with a higher priority task. Okay, so that is the very important thing. You're going to be understood this concept. Task with the tighter deadlines are faster going to be taking the higher priority. So you're going to be assign it by yourself, guys, because those who are what are the tasks which is having a very shorter deadline, you just assign it as a higher priority. Or what are the tasks can able to done by very shorter period, you just assign it as a task period, complete the task as soon as possible. Okay, so these are the things which is going to be happen, sir. Okay, so that's it, guys. So these are the things which we are going to discuss about this. What is task and threat concept, and what are the states in it, and what are the task properties we have been discussed. And tomorrow we are going to be discuss about the task control block, so how one block will be looks like, and what is context switching, and what is ideal task and hooks. Everything we are going to discuss on this next video. So I hope you guys, you have been really enjoyed with this live sessions, and thank you.